Okay, so let us start the new lesson on vectors. So that is called the cross product of vectors, but I think that would be a good motivation if you just look at this video, which is 4 minutes on YouTube, to see how it goes. Then I will come back and try to motivate you. I don't know if I haven't checked the video until the end, but I just want you to see the demonstration done here as an experiment, okay? So I play this video. And of course I will put the
I'm Dr. Bruce.
I will put the link to this video below this video on my YouTube channel. Okay, so let us see if the voice and everything is clear.
Hi, I'm Dr. Bruce DiNardo here in the physics department of the Naval Postgraduate School in Montrose, California. When a charged particle moves through a magnetic field, a force on the particle can occur. This is the fundamental magnetic force. In this video, we will present a demonstration of the effect. In other videos, we will use the concept of the magnetic force to explain other demonstrations, including a jumping wire and a loudspeaker. This is a cathode ray tube, which produces a beam of electrons. The beam is visible due to argon gas in the tube. The electrons here are moving so fast that gravity is negligible. Watch what happens when I bring a magnet near the beam. The beam deflects, which shows that there is a transverse force due to the magnet on the moving electrons. In general, any charged particle that is moving in a magnetic field will experience this fundamental magnetic force. The beam is horizontal outward. When the magnetic field points to the right, the beam bends downward. When we switch the magnetic field, switch the direction of the magnetic field, the beam bends upward. When the magnetic field is pointing straight down, the beam bends to the left. But it has to do that because we can get back to our original case by just rotating the magnetic field. That's where we started from, the beam bending downward. Finally, when the magnetic field and the beam are parallel, there's no deflection. There's no magnetic force. The fundamental magnetic force law quantitatively accounts for our observations. The force is the charge times the vector or cross product of the velocity and the magnetic field. The force is perpendicular to both the velocity and the magnetic field, and the direction is given by the right-hand rule. The force is a maximum when the velocity and magnetic field are perpendicular to each other, and it is zero when they are parallel. Let's check the magnetic force law for the cathode ray tube in the case where the magnetic field points to the right. The velocity is this way, the magnetic field is this way, the force should be up. I bring the magnetic field in, and we see that the force is not up, it's down. So what's wrong? Electrons have negative charge, which flips the direction of the force. So the magnetic force law does work here. A charged particle that is moving in a magnetic field can experience a force, which is the fundamental magnetic force. The force is given in general by the charge of the particle times the vector product of the particle's velocity and the magnetic field. What if we have the common situation of a wire that is carrying an electric current? If the wire is in a magnetic field, there will in general be a force on the moving charges and thus a force on the wire. This leads to many demonstrations and applications. We will show some of these in other videos. It is important to remember that the physics behind these observations comes from the fundamental magnetic force law, which can be demonstrated by a cathode ray tube and a magnet. Physics lecture demonstrations are always fascinating, and the quest for them never ends. This is the physics department of the Naval Postgraduate School, and I'm Dr. Bruce DiNardo. Thank you.
Okay. I don't know how much you got from the video, but I will explain that. At least I just wanted to motivate you that we need what we want to study today. So that is called, mathematically, it's called the cross product. Let me write it here. The cross product of vectors. Okay, here, of course, the experiment was being done on electrons, okay? So, electrons was a little bit confusing, but let me start with something with positive charge, okay? So, but this video showed that at least, so there is an interaction between a magnet and electron, yes? Even though electron has electric charges, and then magnet is a magnetic force, it's producing a magnetic force. Okay, so a magnetic force is a force, so it is a vector. And then electrons are moving in one direction, so they are associated with a velocity. Velocity is also vector, yes? But then we see that actually this magnetic force affects somehow the movement of electrons and then deviate from the straight path, yes? So it means that somehow a force should be exerted on them, otherwise they will continue with the same path, yes? But the direction of the force is a little bit strange. So I mean that this is happening in nature, so it is better to have a mathematical formulation to be able to talk about those situations, yes? So, for the time being, instead of electrons, let me consider a positively charged elementary particle. So let me call it that's positron, okay? Positron. So positron is exactly a copy of electron, but just with a positive charge, exactly, okay? So this is a little bit better to discuss about it here. So we learned that if the velocity of the positron is in this way, so I have a vector involved, the velocity of the positrons, and then what I have is a magnetic force. So what is my magnetic force? For example, let us consider that my magnetic force is acting in this direction. Yes. Magnetic field, sorry, not magnetic force. Magnetic field is acting in this direction. Okay, so I hope that you realize that if this will not follow this path, yeah, so if this is the velocity and I have a magnetic field in this direction, this is not deviated in this direction. It is deviated in a horizontal direction, either to the right or to the left. So I don't know, if you check the video again, then that would be easier for you to understand. So if before having this magnetic field, this, for example, particles are moving to the right, if I turn on the magnetic field, for example, in this direction, yes, if they start deviating like this, then it would be clear that at least the force acting on these particles would be downwards, yes, because they force these charges to move downwards. But you see, it was not the case. When we turn on the magnetic field in this direction, they will not go actually up or down. They will deviate from on a horizontal plane. They go either in that way, or might be they go behind the whiteboard. Yes. So what does it mean? It means that there is a force acting on the electric charge on this plane, either outside or inside. Yes. It turns out that if you repeat those experiments, it turns out that if this electric charge is positive, in this situation, this will deviate in this way. So when I turn on the magnet, so it moves in this direction. As soon as I start this magnetic field, it will deviate outside like this. Yes, this demonstrates something like that. You can just go and check the video. But of course, in that case, because that ray was consisting of electrons, if I turn on this situation, for a positively charged particle, they deviate in this way, but for electrons, they deviate to the back of this whiteboard. Yes? But the situation happens, so at least this is happening in nature, and then we want to have a mechanism, mathematical mechanism behind that so that we can deal with these situations simply. Yes? Okay, so it means that, let us consider for positively charged particle. In this setup, this electric charge will actually deviate in this way. So it means that the force should point outside. So you see the velocity is in this direction. The magnetic field, which is also a vector, is in this direction. If you start doing experiment with positively charged particles, you see that these particles will deviate in this horizontal plane outside. So it means that the force should be perpendicular to these two outside. So if I want to draw, no, sorry, actually I made completely wrong calculation. So if it is positively charged, it goes towards the board. If it is negatively charged, it will come off the board. So sorry, I have to correct that. Okay, so it means that in this situation, the force will actually point, so if this is the tip of the arrow for the force, it points into. And by the way, there is a way to show it in this way. If a vector points into the plane, we show it by this symbol. If the vector points out of the plane, we show it by this. Yes? So that is a standard notation, and this is easy to remember because if it points outward, when you look at here, you just look at the tip of this arrow. And then usually if this is a real arrow for the bow, okay, so then you can see that from the end, you can see something like this. So it means into, it means out of, yes? So this means into the plane, this means out of the plane. So in this situation, it turns out by experiment. This is not something that we can manipulate, yes? We just do the experiment and see that if my particles are positively charged and my magnetic field is in this direction, then the force that I measure by experiment is into the plane. Yes, if that's positively charged. And then if I have the same situation, but I will turn on the magnetic field in the opposite direction, then this particle will deviate in that way. So it means that the force exerting on this is coming outwards. So you can repeat these experiments over and over again by changing the direction of the velocity to see what happens, changing the direction of the magnetic field, changing the charges from negatively charged to positively charged. After all these experiments, you get a new rule that the force is perpendicular to the velocity, and the force is also perpendicular to the magnetic field. This is definitely you get by these experiments. So this new vector is a vector which is perpendicular to both of them. And of course, if you calculate, this is a little bit harder. So you need to find some instruments and some measurements to be able to calculate the magnitude of the force. So we know the direction, but you calculate the magnitude of the force. It turns out to be this. It turns out to be, this value would be the value of your charge, electric charge, multiplied by the speed, not velocity, the magnitude of the velocity, multiplied by the magnitude of the magnetic field, but multiplied by the sine of the angle between these two vectors. Oh, okay, this is not easy task to demonstrate. So you should have precise measuring tools. Okay, so you know about the electric charge of the particles that you send in. You can control the speed of the particles that you are sending in. You can control the magnetic field. We can also control the angle between these two directions. And then you calculate this value and you calculate the force acted on that based on the other calculations. Then you find this relation between these quantities. So actually this combination is interesting for us from mathematical point of view, because might be this happens in this experiment in this nature. So that's a good motivation to see that. Okay, so you see we had something very similar to this combination. Do you remember? If I say what is V dot B, what is the formula? Do you remember? It was the norm of V, the norm of B, and then multiplied by the cosine of the angle between V and B. Do you remember? Yes? So, but by nature, by this experiment, we are forced to admit not only this combination was useful, as we saw, but this combination is also useful. So instead of having cosine, having sine is also useful, at least in this experiment. Yes? Okay. Another point is that this is not enough for investigating this problem, because when you use dot product, even though you have two vectors in the beginning, but the outcome of the dot product is not a vector, it's just a number. Yes? But in this setup, you have two vectors, B and V, but you are interested in the force acting on the particle. So the force is no longer a scalar, it is a vector itself. So you need to know how, you need to find a way to generate a new vector out of two vectors. Here you generate a number out of two vectors, which is not enough for our purpose here, but we want to find a way to generate a vector, the force, out of two vectors V and B. Okay, that is something we want to consider. Okay, in mathematical terms, we want to describe this formula, considering the magnitude and the direction, can be simply summarized into one single formula, writing the force as a vector is equal to V cross product, this is the lesson for today, by B multiplied by the electric charge Q. So that would be the force acting on electric charge Q if its velocity is V and its magnetic and the magnetic field is B. So we want to discuss about this new operation today, and that is called the cross product of vectors. Yes? And the reason that's called cross product, we just show it with cross. Yes? The other one was dot product, this is cross product. Yes? Okay, now we want to define it formally. So let me just do it mathematically. So definition. So let U and V be vectors. The cross product you have to put this cross, you see, this is not optional. The cross product U cross V is defined as follows. So we consider some cases. We say that if U, so there is this V has nothing to do this with velocity. These are mathematical vectors. I call one of them U, one of them V, and I want to define what does mean U cross V. I say that if U is the zero vector, we define it to be zero. By the way, that's also confirmed by the experiment. Do you see that these electron rays were actually moving without deviation if the magnetic field was not there? So if the magnetic field was zero, what you expect about the force should also be zero. Yes, we follow the same thing. We say that is defined as follows. It is the zero vector if u is the zero vector or v is the zero vector. There is an or, it was in the experiment. Can you say when? In one case, do you remember in the video? That person had a magnet in hand, but oriented in a way that there were no deviation. Do you remember in the video what was that?
It was parallel.
Parallel, yes? Yeah, that's exactly the case. So it is the zero vector if the u is 0 or v is 0 or u is parallel to v, yes? So you see that everything is more or less forcing upon us by that experiment. So that was the motivating probably. I haven't checked the history, but I think that is probably a very good motivation for studying the cross product of vectors. So do you remember that when that person was keeping the magnet parallel to the velocity, there were no deviations? So if I ask you to cross product two vectors, first you check if one of them is 0, you say that the answer is the 0 vector. If they are parallel, you would definitely say that the cross product is the 0 vector. But what happens if that's not the case? Number 2. If u is not equal to 0, v is not equal to the 0 vector, and u is not parallel to v, then u cross v is defined to be the vector that is perpendicular to both vector u and v with the magnitude u cross v equals to norm of u, norm of v, sine theta. Theta is the angle between them. Such that its direction follows the right-hand rule. Follows the right-hand rule. So this I have to explain. It's hard to explain in words, so I will explain it orally. So the right-hand rule. Such that its direction okay, so if I give you two vectors and I ask you to determine for me u cross v, then you first think, if u is 0, the answer is the 0 vector. If v is 0, the answer is the 0 vector. If u and v are parallel, the answer is the 0 vector. But if not, you have to follow the second item. So what does it mean? Assume that you need to, so for example, let me consider, this is vector u, and this is vector v. Yes? I want you to imagine it in this way, that okay, so these two vectors are non-zero and non-parallel, so they will be in one plane. So we can consider that they are lying in one plane, yes? If I have two vectors, look here. So this is one vector, this is the tip of the vector, and that's the tip of the vector. If two vectors are non-zero and non-parallel, so they are of this form, yes? Either in this form or in that form, it doesn't matter, yes? But then, even if this is in this form, if you remember, I told you that there is no location associated with the vectors. So this situation is equivalent to this situation if I parallel transport them. And when I parallel transport them, and if they are not parallel, then they will actually form a plane for you. And that plane is that plane, yes, that I am drawing. So in principle, if this is vector u and this is vector v, this plane is the plane of my hand, so it would be perpendicular to the plane of the whiteboard, okay? Then it means that when you want to cross product u by v, this becomes a vector which is perpendicular to both of them. So let me just draw it here. So the vector u cross v would be in a direction which is perpendicular to this one, yes? And is perpendicular to this one. I don't know, can you imagine that? So that is perpendicular to both of them, okay? So if I want to be more precise, I have to draw a dotted line, yes. That's behind the other one. Okay, and so that would be the direction of u cross v. A direction which is perpendicular to both of them. But what is the size? The size, you have to calculate it using this formula. So you measure the length of this vector, it becomes magnitude of u. You measure the length of that vector, and then you measure the angle between these two vectors, which is theta. And then you put them in this formula. This number multiplied by this number multiplied by this number, it gives you a number. And that is the, for example, assume that that would be a number, I don't know, you should separate it either here or there. But the point is the right-hand rule. The right-hand rule tells you that if you are multiplying u from the left to v on the right, you have to take your right hand and then bend your fingers in a way that this will rotate u and put it on v from the angle between them, not in the other direction. Because I can also take u and rotate it from this direction and put it on u. That is not what I mean. You have to rotate u through the angle between two vectors and put it on v. So you need to bend your fingers in that direction. Then your thumb will point the direction of the cross product of u by v. Yes? So that would be in this direction. In this setup, u cross v is in upwards direction. How much? Up this number, for example. So this becomes something like that. So, assume that I have this vector. So this vector becomes u cross v. If I ask you what is this length, you can give me a number by calculation. U, norm of u, norm of v, multiplied by the sine of the angle between these two vectors. So is that understandable? Yes, I have seen that in physics text. I don't know, they use these kinds of fingers. It's a little bit confusing. This right-hand rule is actually very simple to use. Yes? Is that clear? So u cross v is a vector, so you have to consider it should be a little bit harder, because in the dot product the answer is a number, but in the cross product the answer is a vector. And if you want to introduce me a vector, you need to talk about the inclination of the vector, you need to talk about the direction of the vector, you should also talk about the magnitude of the vector. So that would be a little bit harder. Yes? But this is forced upon us by that, at least that experiment. You see that in nature something like this happens, yes? Is that clear? But let me ask you something, so to understand to see how much you understand this. Do you think that this operation is commutative? So what do I mean? I mean that if I give you two vectors, u and v, do you think it matters I multiply in this way or I multiply in that way? For the other operation that we had so far, it didn't matter, yes? U dot v is the same number as v dot u. Yes, so we learned that the dot product is commutative. Yes? Is the dot product commutative here? Is the cross product commutative here? Yes or no, and why?
I would guess.
Yes?
No.
No?
One of them would be the other there.
Exactly. So it is not commutative. It's anti-commutative. Why is that? Because if I ask you, show me vector u cross v, it is on this board. Now I ask you, show me v cross u. Okay? So what you have to do? You have to tell me the inclination, what is the line along which this lies. It doesn't change. That is the same line. Because it is supposed to be perpendicular to both of them. So that is only one direction, yes? But if I ask you about the magnitude, do you think the magnitude is different? The magnitude of this one is the magnitude of the first one multiplied by the magnitude of the second one multiplied by the sine of the angle between them. Nothing has changed. So the magnitude also remains the same. But now if I want to use the right-hand rule, I am not allowed to bend my fingers in this direction because I am supposed to bend my fingers in a direction that takes the first vector onto the second vector through the angle between them. Yes? So it means that the angle between them is this. I want to bend my fingers in a way that takes v to u in this, through this angle. So what should I do? If I want to do it like that, I am moving v from this direction, which is not allowed. So I have to move v in this direction. So how should I bend my fingers? If I bend it in that figure, the rotation would be here. So I have to bend it in the other direction. Yes? So this means that this is the way that I have to bend my fingers in a way that moves v through this angle to v. So then it points downwards. Yes? So it means that this vector and this vector have the same magnitudes and they are lying on the same line, but one of them points upwards and the other one points downwards. So it means that they are, what is the relation between them then? If I have two vectors parallel, yes, with the same size, one upwards, the other one downwards, it means that they are negative of each other, yes? So this is negative. So is that clear? So the cross, this is called this operation is anti-commutative. So it means that if you interchange, you have to have a minus sign there. Is that understandable? Yes or no? Okay. Now, because by my experience, this right-hand rule is a little bit confusing, let us do some exercises on that. First of all, make sure that you really understand how to bend your fingers, yes? Okay. And then remember this symbol. I told you that. This means that this symbol means pointing outwards. This symbol means pointing inwards. Yes? Is that clear? So let us first do one exercise. Okay, if I ask you, one question. If I ask you what is the main difference between this new operation and the old operation, what's the main difference? Of course, there are many differences, but what is the main difference? Yes, Kevin?
That the result is a vector.
Yes, that the result of the cross product is a vector. The result of the dot product is a number. Yes, so this tells you how to generate a vector. But of course, we knew about how to generate a vector from vectors. Yes, if I add two vectors, the answer becomes a vector. But what motivated us to think about this strange way of generating a new vector was probably that experiment. Yes, because if I have vector v here, if I have vector b here, if I add them, it becomes something like this. and then you saw that the deviation was not in this direction, the deviation was either in that direction or in that direction. So addition of vectors was not enough for our purpose, so we have to introduce a new concept, yes? Okay, so now let me go and then try to solve this example. To make it simple, instead of imagining in this space, I put my vectors exactly on the whiteboard plane, and then you tell me the cross product either pointing out or in by putting these symbols, yes? So let me see. I have already prepared some ideas. So example. In each case, U and V lie on the whiteboard plane. They both lie on the whiteboard plane. Is the spelling of white correct? Yes? Yeah. Whiteboard plane. Okay. Determine the direction of U cross V. Okay? So let me draw some pictures for you. So number one, let me draw U in this way. I draw V here. So I will draw them and then you can start solving. Don't imagine it. So U and V are both on this plane. So U cross V either goes outward or goes inward. You need to realize that. So number two. Yeah, hopefully that's enough. So I can give you a little bit of time to think. Yeah, don't spoil the example. So this is in this exercise, it is important first of all, because you know that we have to bend our fingers in a way that takes U to V along the angle between U and V, not any kind of rotation that you like. Yes? For example, in this case, if I ask you what is the angle between these two vectors, what is that one? This angle is exactly the angle between two vectors because there was a definition for the angle between two vectors. You have to draw them from the same point, and then the smaller angle is the angle between them. Yes? So that is extremely important to imagine that you are drawing in them from the same point and then apply this rule. Yes? So let us just do that together. So here, what is your opinion? By the way, they are on the plane. So they are on this plane of my hand. So where is it? Inwards or outwards? Yes, good.
Inwards.
It's inwards, yes? Because this is the way that you have to bend your fingers. Let me make it clear. This is the angle between two vectors. So I have to bend my fingers so that takes U through this angle to V. And then you see that my thumb is pointing in to the plane. Yes? So I would write this is what? this direction. I want you to understand that. Is that understandable? But for the next one, what I want to hear from you. If you start doing right away, that is wrong. If you want to do it like this, it's wrong. Yes, because this is not the angle between U and V. Yes, the angle between U and V happens if I draw them from the same point. So if I parallel transport it in my head, okay, so then the angle between these two vectors is this angle. Yes, so I have to bend my fingers in a way that takes U to V through this angle. So the rotation should be in this direction, yes? So then if you see, if I rotate U to V, it points outward. So this is extremely important to understand, this direction. Is that understandable for you? Because in this case, U cross V is outwards, but V cross U will be inwards, yes? V cross U, I have to change the rotation in that way, so it becomes inwards. Yes? Is that clear? Okay, so what about this number 3? Yes?
It's inwards.
I need to check myself. It is... I don't think so. Yes? So it is... It's outwards. Yes? Why? Because, of course, in this case, you need to draw them from the same point. So if I parallel transport this, this would be U. If I parallel transport this, this would be V. And then this would be the angle between these two vectors. And I have to bend my fingers in a way to rotate U onto V, so the rotation should be in that way. So this becomes outward. Yes? So this is also this symbol. What about the next scenario? Yes?
Inwards.
Yes, it is inwards. Yes, why? Because you have to draw this one from this point. Yes? And the angle between two vectors is that one. But in which direction? I have to bend my fingers in a way that rotates U onto V through this angle. So the rotation should be in that direction. So then this becomes inwards. Yes, you are right. Yes? Understandable? Everything? And what about this scenario?
Also inwards.
It's also inwards, because if I parallel transport it here, then this would be the angle between the vectors. I have to rotate it in a way that turns U into V, so it becomes in this direction. So that becomes inward, yes? What about number 5?
Zero vector.
Yeah, so there is no direction associated with that because they are parallel, or I intended to draw them parallel, so that's the zero vector. So there is no direction associated with the zero vector. That's just it. Is that understandable? But now let me test your understanding, okay? First of all, this is, so do you remember we have some operations, addition, subtraction, and then we have a number multiplied by a vector. We didn't use any symbol for that. That is a little bit unfortunate. We cannot put anything between them. If I put cross, that would be a little bit mysterious. It will be confused with this cross. If I put dot, it will be confused with the dot product. So it means that you shouldn't put anything between a number and a vector. Yes? And then we learned the dot product. Today we're also learning the cross product. So this symbol is meaningless. Yes? Because the dot means that on the left and the right you should have two vectors, but the answer would be a number. Yes? So this is meaningless. So the same situation, do you think that this is meaningful? It's also meaningless. So you don't have any thing like that. So this is meaningless. But tell me, is it meaningful or not? Is this combination meaningful or meaningless? Yes?
It's meaningful.
It's meaningful because this dot, on the left hand side I have a vector, on the right hand side I have two vectors added together, so it becomes a vector. So that's me. What about this new that we learned? is this meaningful or meaningless? That's also meaningful, yes? But the outcome of this is a number, the outcome of this is a vector. So these are meaningful things. But now, let me ask you something. Is this meaningful or meaningless? Yes?
Meaningless.
Why?
Colorful.
Yes?
It is meaningful.
It's again meaningful, yes? Because this dot is sitting between two, is supposed to sit between two vectors. The left hand side is vector u, the right hand side is a cross product of two vectors, but we learned today the outcome is still a vector. So it is completely meaningful to ask what is the dot product of this vector with the cross product of these two vectors, yes? Okay, now I want to ask you a question. I give you two vectors. It's extremely important to know this. I give you two vectors, u and v. I don't tell anything more about these two vectors. I don't give you anything about the sizes of these vectors. I don't tell you anything about the angle between these two vectors. Now I ask you, can you say something about this particular combination? First of all, is this combination a number or a vector at the end? It's a number, yes, because u is a vector, u cross v is a vector, the dot product between two vectors is a number. But what that number is, can I say something for sure about the outcome of this without knowing anything about u and v? You need to imagine a little bit, and you need to remember something, of course, from the dot product.
It's zero.
It's zero. Why?
Because the 90 degrees between you and nu.
Yeah, they are perpendicular. We just define, if I tell you this is perpendicular to u, you have to agree with me because that was the definition of u cross v. So remember, u cross v is perpendicular to each one of those components. It is perpendicular to u, it's perpendicular to v. And from the previous studies we know that if two vectors are perpendicular, the dot product should be 0 as a number, yes? So this is without knowing anything about these vectors, this combination is exactly equal to 0. What is this combination? What is this combination? Just be quick. 0 again, yes? Because u cross v is perpendicular to both of them, yes? Is that right? What is this one? First of all, tell me, is it meaningful or meaningless?
No.
Is it meaningful or meaningless?
Meaningful.
Meaningful. Why? This one makes sense. That's a vector. Let us investigate what is on the right-hand side. What is on the right-hand side? Is it meaningful itself? This one is a vector. This one is also a vector. And then I am cross-producting two vectors, so it is meaningful. And the result is again a vector. So I have a vector on the right and I have a vector on the left and I'm dot producting them. So that's completely meaningful. What is the answer? Vector or a scale? Number immediately.
Number.
Number. Yes, what that number is?
If it's perpendicular to u and v, it should be 0.
It's 0 again. Yes, that's 0. So let me tell you. Let me call this one capital U. Let me call this one capital V.
Oh.
And then the same thing. This is again capital U. That's the same combination. So that's also 0. Is that right? We don't know anything about the vectors involved. Whatever they are, this combination is exactly equal to 0. Is that understandable? Yes? Okay, good. So that is extremely important. So let me write down somewhere here for you. So let me write this as a remark and then leave this. Okay, so let me write remark. For any two vectors u and v, we have u dot u cross v is equal to v dot u cross v is equal to 0, number 0, yes. That's good to remember. This is an important thing. Now let me give you some simple questions. So example, this is very simple. Let u and v be vectors such that norm of u is given to be 3, norm of v is given to be 26, and norm of u cross v is equal to 72. If the angle between u and v is an obtuse angle, so let me write, if the angle theta between u and v is an obtuse angle, determine theta. Okay? Do you want to give it a try? I think it's easy. So please try to do it yourself first. Yes?
Obtuse, is that when it's bigger than...
Between bigger than 90 is smaller than 180.
Okay.
Yes. Alright.
So we could just say... that
I shouldn't say determine theta. I should say determine a dot b, u dot v. So you really don't need the exact value for theta. You need to know some information about theta using these pieces of information, but what I need, you should be able to find u dot v exactly.
Okay.
I think it is possible now, yes? Sorry for that mistake. So here, let us see. Do you remember today we talked about this one? This is not something that you knew before, yes? So do you remember the formula? What's the formula? The norm of u cross v is equal to norm of the first one, norm of the second one, but multiplied by the sine of the angle between them. By the way, before continuing, do you think this is problematic? Because you know that sometimes sine turns out to be negative. Yes, if you are in the third quadrant and fourth. And then if I multiply a negative number by this one, by that one, because these are positive, it becomes negative. And then the norm of a vector cannot be negative. Do you think I need to put absolute value here to be on the safe side, or I don't need it? Yes?
You don't need it, because if it's in the third or fourth quadrant, the angle between them is...
The smaller one. So the angle between two vectors is minimum 0, maximum 180. It cannot be larger than that. So we really don't need to overemphasize by putting an absolute value. Okay? So then this one is given. These and that are also given. So I don't know what to put, but among numbers, let me put this, yes? 3, 26, and then sine theta is missing. Agree? Then it means sine theta is 72. Okay, I can divide it in my head, yes? 72 by 3 is 24. 24 divided by this, it becomes 12 over 13, yes? So this is the angle sine of my angle. Yes? And then you know the famous formula. You had the exam yesterday. It doesn't seem a very good exam, but it was probably, yes. Let me continue later about the exam. So cosine squared theta plus sine squared theta is equal to 1. And then cosine squared theta we don't know. But this 1 to power 2 is how much? 144, 169 is equal to 1. Yes? You move it to the other side. 1 minus that 1 is how much? Is 25 over 169. Yes? Then, this is not under my control. I have two answers. One positive, one negative. This is why this extra piece of information is provided in the problem for you. Because in general, both of them are acceptable. Yes? Cosine theta becomes plus or minus the square root of that, square root of that. Yes?
When I solve it my way, I only get one answer. I don't understand why.
No, this we have to come back to you. Let me finish this one. Definitely, you should be able to get two answers. I don't know. Might be you have some geometry arguments involved in your argument. Let us see. But here, in principle, both of them are acceptable, even for vectors, because I told you the angle between a vector is minimum 0, maximum 180. So it is in the first or second quadrant. If it is in the first quadrant, cosine turns out to be positive. If it is in the second quadrant, cosine turns out to be negative. So I really need an extra piece of information to rule one of them out. Otherwise, I don't know. Both of them in principle are acceptable. Yes? But because theta is an obtuse angle, this implies that cosine theta is the negative one. Yes? And then I want to calculate u dot v. What is u dot v? The u dot v is norm of u, norm of v, cosine of theta. Norm of u is 3. Norm of v is, of course, I don't know what to put between them. I have to put something, yes? So 3 times v, what is norm of v? 26. And then dot this number, minus 5 over 13, yes? And this one and that one are simplified, so the answer would be minus 30. Yes? So that is the exact answer, minus 30. Understandable? Yes or no? Okay, now what is your argument?
I mean, what I did, I took sine inverse. So, I mean, I'm sure. Do the something. Yeah, I mean, I got theta first.
No. This doesn't work. Because if you do sine inverse only gives you the angle in the first quadrant.
Okay.
So it doesn't know, calculator doesn't know about another possibility. We learned it in trigonometry as well. Okay, you were not in my lesson. But sine inverse, if you use this symbol, sine inverse, then this only gives you one angle in the first quadrant with the property that sine is equal to 12 over 13. But there is also another angle in the second quadrant with the same value that the calculator will not give that to you. Okay, but in that case the calculator will give you which one? Will give you the positive one. So then you will end up with the positive value. That's exactly the wrong one. So this, you shouldn't try the calculator, you shouldn't trust the calculator. This is the real. So, but the reason, if you want to understand, this by convention is a function whose outcome is from minus pi over 2 to pi over 2. Yes, this is a little bit, they haven't discussed about these things in high school, but this sine inverse, which is implemented in the CPU of the calculator, calculates the angle whose sine is equal to this, but the angle from minus pi over 2 to pi over 2. It doesn't know anything about other angles. In this case, we exactly want the other angle.
Makes sense.
Yes? Is that understandable? Okay. So, I think it's a good point to stop here, but we will continue with this topic a few sessions more because that's extremely important, yes? And then the notion of vectors, geometrical notion of vectors will be finished. Then we have to go to analytical way of doing vectors, then it becomes simpler. But then, of course, we want to go to space, so we want to go to 3. We want to go to 3 dimensions, yes? Yes, we will have 3 axes, yes? X-axis, Y-axis, and Z-axis, yes? And that's also interesting. Then after that, we decide in which direction we can move, yes? We can continue with this lesson, going to discuss about planes and lines in a space, or we can choose another topic. Let us see how it goes, yes? Okay, thank you very much. And now,